Welcome. You are in room C. Please set your phones to mute, do not disturb. And you are going to see automating computer security. And please give a big round of applause for Tyler Nighswander.
All right, thanks. All right, so I'm going to talk about automated computer security. This is an artistic representation of what we're going to be talking about. All right, so the first question is, when we're doing computer security and we're trying to automate bug finding, things like that, why do we need computers? So this is actually not a very difficult question. We have way too much software. Some people a long time ago decided that C and C++ were great languages and wrote a lot of it in C and C++. And all of the software is just full of bugs. Not just the C and C++ software, all of it. So we have humans. Humans can audit software. This is great, but humans don't scale very well. It's hard to hire 100 people that are good at computer security. It's just not going to work. And turns out that scaling is one of the few things that computers are actually pretty good at. You can buy bigger racks, you can buy more racks, you throw more compute power, easy. So the real question is, if we want to automate computer security, the first thing is, can we actually do this with computers very well? So we'll start off talking about this question, automating computer security, and can we do it with computers? So we're going to use the Cyber Grand Challenge as motivation. How many of you have heard of the Cyber Grand Challenge, out of curiosity? Okay, cool. So I'll go into more detail on it. So short version is it's basically offensive and defensive kind of security tasks on strict binaries. There's a third-party referee that's scoring it. It's not like the company that I work for ran it and to make us look good or something. So it's kind of the best way to look at the state of the art in program analysis and things like that and see how far along have we come in automating this task. So DARPA is an organization in the United States run by the government. They do lots of kind of fancy things. They've helped invent things, internet, GPS, stealth technology, Tor, etc. And they host these cool challenges. The most well-known example is the DARPA Grand Challenge, which was for cars in about 2007. So here's an example of one of those cars. It doesn't look like much. There's actually no room for a human to sit in. But it turns out eventually this led to the self-driving cars that are kind of becoming a thing today. And the same people who worked on the Grand Challenge for DARPA work on the Google self-driving car thing. So the idea was let's do the same thing for computer security and model it after a capture the flag competition, because this is kind of a great way of measuring ability in computer security. And because it's the US government, they throw lots of stupid money at it. So offer $750,000 to the top 7 teams who qualify. The team that wins in the final contest gets $2 million US dollars. And one of the nice things is it's not like you sell this to the government. There's no intellectual property stuff. It's just they want to push the technology. So this is a Cyber Grand Challenge. This is also a good point to talk about myself. So I am a CTF player at heart. I've been playing CTFs about 7.5 years. PPP is one of the best teams, hard to measure. But anyway, I also graduated from Carnegie Mellon University, which is where that robotic car from that last slide was on. So it's a school that does a lot of these kind of DARPA challenges. And I work at a company called For All Secure, which has been basically works on automated security stuff. So CGC is kind of like almost like made for me. So it's super awesome. So we'll talk a little bit more about the details of this. So it's an attack defense CTF format. So the way this works, if you don't know, you've got a network, a bunch of computers on the network, you have a referee, and then you have players. And so the way that this is set up is you've got flags on the computers for the players associated with certain challenges. And then to score points, you break in through the network, capture the flag, and submit it to the referee. And then maybe you'll get some points for capturing the flag, and the team that lost the flag maybe loses some points as well. There's some other things. So normally, these are associated with services, so you have to keep your services running. So the referee might poll and make sure that it can talk to something. So if you have an email server, maybe it'll go in and make sure it can properly send an email. And if something happens and your service is down, maybe you tried to patch it and you failed or something like that, the referee will try to talk to you and say, you're doing something wrong and you lose some points. So in CGC, the scoring is based on the same notion. So you've got security, so you lose points if anyone ever exploits you. Offense, which means if you exploit other teams, then you get points. And availability, which is making sure that your services are running. So if you decrease the performance of the program that they gave you, or if you decrease functionality, you can no longer send emails, for example, then you also lose points. So the way this is set up is a lot different from a normal attack defense CTF, if you're familiar with them. So instead of having a network where the players connect, DARPA runs everything. So if you want to patch a binary, you give them a patched binary to run. If you want to exploit something, you give them a program that exploits something. So no longer is it kind of this somewhat simple network model. It's kind of like this. So instead of having humans connected to the network, it's just computers. And then the referee kind of simulates a normal attack defense CTF. So if you want to take an action on the CTF network, you talk to the referee over an API, and they'll simulate the actions and calculate the scores and everything. So we won't talk too much about the patching, but I will briefly mention it because it is interesting. So the availability scoring is very strict. So as I mentioned, you lose points if there's functionality failures. So these are measured based on what we call service polars. So it's kind of like unit tests. So again, if you imagine email, whoever wrote this email server might also write a test for the program, which will go in and make sure it's still functioning. However, they don't give you a specification for, they don't say this is an email server, this is the specification it should conform to. They don't give you tests and say this is the test that it should pass. They just run the tests, and you can maybe observe network traffic, but that's all the information that you're given. So this is pretty difficult, especially when you think of automated tasks, which normally you have specifications or something that you try to check. You also lose points if your memory usage or CPU usage increased by 5%. This is actually really crazy if you read academic papers or anything. So if we look at something like 15% overhead, you get 70% of your score. And this is interesting because if you look at like state-of-the-art taint tracking or something like that in academic papers, that's about a 15% overhead for like the best things that they have. And that's effectively not feasible here. So you have to come up with some really clever solutions. And just a few more kind of nitty-gritty details. So the competition was run on a new executable format. It's basically an ELF, but they don't call it an ELF. There's only 7 system calls, so you can still do some stuff, but it makes running code more safe. So again, because DARPA's running stuff, this allows them to run code without having to worry about you doing weird things. It's effectively a sandbox. It also is very nice because if you're writing tools and you want to automatically analyze things, you don't have to model 100 system calls or whatever that Linux has. You can just model these 7. So the first question is, well, what's an exploit in something like this? Because you don't have, exec or fork, so you can't. There's no file system. So there's 2 types. The first is you control a register and the instruction pointer. So this is basically their way of saying it looks like you could exploit it if it were a more traditional system. The other type is if you leak sensitive data out. So they mark a certain region in memory, say this is sensitive data, and if this is ever sent over the network, if you can demonstrate that you can read it, so effectively just Heartbleed. That's basically the motivation for that. So one interesting thing is, even though there's only 7 system calls, there's still a lot of really complicated things that you can do. So programs can have several binaries communicating, so it's not just one program. They can communicate over file descriptors, and you can have 7 programs all talking to each other. You can have user space threading. You can have, non-determinism because there's a random syscall. So, it seems like 7 system calls is just going to make really boring programs, but you actually get a lot of cool things. And all of it is C or C++, compiled down to x86 assembly. I guess technically x87 because there's floating point as well. So just to kind of demonstrate this, they've several real world bugs that you can basically rewrite the kind of the vulnerable part of the code in the same thing. So Heartbleed, link exploit, crackadder, SQL slam, whatever. So these were some example problems where they rewrote the kind of original bug in this framework, which is really nice. Cool. So the system that our team created was called Mayhem. So we won, so that's exciting. Yay, we're all very happy. So it's getting darker. So the overall architecture of the system's somewhat interesting, but it's basically the same thing everyone else did, which is, you have a lot of components working together, symbolic execution, fuzzing, stuff like that, and kind of a centralized database. So anyway, this is basically the rough overview of CGC. So we're just going to talk a little bit about the offense part, so basically finding and exploiting bugs, because this is kind of the more interesting part, in my opinion. So the first way that we have, the first technique for finding bugs is called symbolic execution. So this is basically, if you look at academic papers, this is kind of what everyone's always talking about. It's kind of the state-of-the-art thing. Basic idea is you take a program and you try to represent it as a symbolic expression, and then you use a SAT solver or an SMT solver to generate inputs. So we'll go over a bit of an example for that. So let's take this one function, and let's say we want to symbolically execute it. So first we say, well, what are we marking as symbolic? Let's just take the first argument. And then we can make something kind of like a control flow graph. So we look at all the conditions, and then they break apart, and we can follow this along. So these gray boxes are what we call path constraints. So these are basically conditions that determine whether the program will execute one way or another when you give it concrete input. So if you want to look at symbolic execution, maybe you want to go to a particular place. So let's just take that return 0 down there. What you'll do is you'll start at the top, and you'll create a path all the way down and add the constraints. So maybe the first thing is we want it to take the green branch here, so the length of argv has to be greater than or equal to 3. And then the next part of this path, well, we don't want to take the true branch, we want to take the false branch. So we'll negate this condition and add this to our path constraint. And then finally we get to the bottom, and this is kind of the end of our graph traversal. So we go to an SMT solver and we say, all right, here are my constraints, can you give me a solution? And maybe it comes up with something like that. So that's the basic idea behind symbolic execution. So the other thing is fuzzing. So this is basically the technique that everyone uses in industry or kind of the real world. And the basic idea here is you just take some values and you just throw them at the program. To be successful with this, you also probably want to instrument the program. So basically what this means is you look at the internal state of the program as it's running. So there's a few techniques to do this, but the basic idea is, if we take another little block of pseudocode, we'll make kind of a pared down thing that looks kind of like a CFG. If you look at the probabilities, for example, that a path is going to ever get hit, if these are integers or something, it's very rare that you're ever going to guess, 42 as a random integer value. It's just, the probability is 1 in 4 billion. And so the issue is, if you want to get all the way to that print statement at the bottom, and you have no insight into the program, it's actually not it's not, 2 to the minus 32 probability, it's 2 to the minus 64 probability, because you're going to have to guess both. However, if we instrument the program, we can do a little bit better. So, let's say we'll instrument all blocks, we throw some values at the program, and we see what happens. So maybe we throw these random numbers, and we hit the return 0, not very interesting. We throw something else. Maybe we've guessed the B value correctly by chance, but that doesn't really mean anything because we're executing it concretely. We just throw the values at the program, and we still get to the same return 0. But eventually, maybe we guess 42, and now we get to this interesting place. So if we instrumented the program, we'd say, oh, we just did something really cool and interesting. We got to somewhere we've never been before. We should keep working on that. So now you keep throwing values, keeping a constant, for example, and maybe eventually you'll get there. So in some sense, we've taken what would have been a 2 to the minus 64 probability and turned it into something maybe like 2 to the minus 34 or something. So a lot more feasible. Cool. So the basic idea is you use this instrumenting to get a lot deeper inside of these programs. So instrumenting, it's not clear what the best way of doing this is. There's a lot of research still in here. If you have binaries only, so again, compiled programs, not source, there's a few kind of different engines that you can use to look into these programs, but they all incur a pretty big slowdown. And this is an interesting point about fuzzing. The whole point of fuzzing is to just be really fast. So if you try to add a bunch of stuff and make it really smart, it just makes everything slow and you find fewer bugs. So just to quickly reiterate, so we've got fuzzing, symbolic execution. So fuzzing, it's great. It's pretty easy relative to symbolic execution, which is really complicated both to develop and to run because it has a lot more infrastructure. For fuzzing, you execute a program very, very quickly, so something like 10 to maybe 10,000 times per second. Symbolic execution, it's a little bit weird because you don't exactly execute the program with data. You generate a bunch of constraints and you give them to an SMT solver. And maybe this returns in a second, maybe it returns in a year. So you have to be a little bit tricky. It's tricky to make this work properly and adding timeouts and things like that. So fuzzing, it's kind of, even with instrumentation, it doesn't really know anything. Maybe it'll throw a random value and find out that that value is interesting, but it doesn't know right away that 42 is a good value to send the program. On the other hand, symbolic execution actually knows what's going on. So it'll say, I should take 42 because that will change this branch condition. So fuzzing is nice because it's very light on resources. You just throw a bunch of CPUs at it. As long as you can run the program, you can probably fuzz it. Symbolic execution is a little bit worse. You've got a lot of overhead due to SMT solving, due to special tracing, all of that. So it's very resource intensive. So fuzzing, effectively, you take the shallow paths, very shallow in the program. You can explore those quickly. Symbolic execution, you go to the deep paths, but it takes a long time. Fuzzing, you have to worry about stalling. Maybe you stop uncovering new paths because all the new conditions are behind something very difficult to guess by throwing random data at it. Symbolic execution, well, it turns out that the state of the program is exponential with the size of the program, and so trying to explore every single path is just not feasible, and so you have issues with that. So there's pluses and minuses of both. So the main idea that some people have started doing now, including us, is try to combine the two. So do fuzzing as well as symbolic execution. So the hope is that you can combine the best of both worlds. So you fuzz a program, and hopefully this uncovers lots of the shallow paths. And at the same time, you also use the symbolic execution to find the deep paths. So since you're already, doing both of these, then you kind of share the inputs between the two of them. So when you run something, you'll get a new input. And you have to figure out, oh, this was interesting. So just like we saw with our instrumentation, which said, oh, you hit a new basic block, this is interesting. You do the same thing here, and you say, okay, symbolic execution uncovered something new, give it to the fuzzer. Fuzzer uncovered something new, give it to symbolic execution. So you just share the interesting inputs back and forth. Cool. So you find lots of bugs, hopefully, and now you have to exploit them automatically. So how do you do this? It turns out that this actually isn't that hard if you are already doing symbolic execution. So basically all you have to do is, in addition to the path constraints that you already had, so let's say, again, a equals 42, maybe you also say a equals 42 and EIP equals 41, 41, 41, 41. And if you're able to satisfy this set of constraints, that means that you're able to control the instruction pointer of the program. So, you can basically just use an SMT solver here, and that will magically solve this for you. There's going to be a lot of cases where this doesn't work well. So you can do some cool stuff where you combine fuzzing and symbolic execution to kind of get new crashes. So if you start from, maybe an invalid memory read or something, you might be able to symbolically execute that and change the memory read to succeed, and then explore a little bit deeper in the program and move on. And then again, you just use symbolic execution to generate the exploits. So it turns out that this actually works pretty well. I'm always kind of surprised at how well it works. So we'll just go over a quick example. So here's a program, not sure how visible it is, but this is from DEF CON finals this year, just an excerpt, not the whole thing. So finding the bug is, I'm not expecting you to do it, but it turns out there's basically a null byte overwrite kind of at the end here. So all you have is effectively a single null byte overwrite. So how do you exploit this? So what our system ended up doing is it took the lowest byte of our saved base pointer in the stack frame of the callee, and it overwrote the lowest byte with a 0. And then the stack frame above that restored that EBP, which was now incorrect. And then when it tried to reference a buffer, that buffer was now in the wrong place. So future writes to that buffer, now clobber memory. And then you send a command to do another write, and then overflow the buffer, overflow EIP, and that's it. So, if you're an avid CTF player, you'd say, like, okay, like this is the sort of thing I could totally do. It's not easy, but it's not, impossible. It's not, writing a browser exploit type of thing. But it's pretty interesting to me. So our system, for example, found and exploited this bug in 105 minutes, which is actually quite fast. I don't have any numbers to say how fast a good human would take, but I would guess it would not really be any faster than 105 minutes to find and exploit that bug. So that's pretty cool. All right, so some lessons learned. So computers can be a lot faster than any humans. This is especially true when you're dealing with, simple bugs, not complicated things. And this really shouldn't be surprising. I mean, we know fuzzing works pretty well. You throw in some other techniques, you should be able to exploit stuff, etc. One thing that a lot of people are surprised by is this is actually relevant to real systems. So, CGC, only 7 system calls, whatever, no one cares. So our system, for example, to port it to CGC, we just removed all of the normal Linux stuff. But our system runs on Linux just fine. So a lot of people think that making that additional step is another few years away. That's not true. And computers find actually more bugs than someone might find more bugs than people might originally think. Especially a lot of things that humans might overlook. So, computers are a lot more systematic about exploration compared to humans who kind of look for known patterns. So this is pretty interesting. So, all right, why do we need computers, not just in general, but really soon? So the first issue is Internet of Things. Internet of Things is terrible idea, but it's going to happen. And part of the issue is, instead of switching to fancy new languages with memory protection, we're going to go back to the 90s and turn off all of the security features because we're trying to put it on devices as cheap as possible. And probably the only way to keep up with this is going to be to try to automate a lot of the searching here. And this is a great candidate for automation because a lot of these bugs are probably going to be really easy bugs because they're terrible. So another thing is fuzzing is working really well. So there's a lot of nice projects like OSS fuzz, and slowly, if you look, programs are getting more and more secure. All the shallow bugs are slowly getting uncovered. So this is great because it means bug finders have to step up their game. But this also means that the way forward is going to be to improve these techniques. We've seen they work with fuzzing. We need to throw in other things like symbolic execution. But on the other hand, fuzzing does still find tons of bugs, and triaging them currently is a really terrible process. There's some automated tools you can use to help, gauge which ones you should look at, but having automated systems that did this would be much better. So automated systems can help with all of these things. So at this point, most people are like, yay, computers are going to solve all of the problems and everything's going to be great. So now we're on to the next part. So why that is completely untrue. So we'll start with the lessons learned that we mentioned, and we'll add a few more things. It turns out, yes, computers find lots of bugs, maybe more than expected, but they're not magical, and they still miss a lot of bugs. Maybe even the bugs that that humans find very easily. There's a lot of tricky bugs that computers don't really stand a chance at exploiting. And computers have difficulty scaling to very large programs, not necessarily as a fundamental limitation, but at least with current technology. So let's start talking about automatic exploit generation. So we know it's possible to generate non-trivial exploits because we went over an example. It turns out this can do a lot of cool things. So stack canaries, maybe people think, oh, stack canaries would prevent automatic exploit generation. That's not really true. In fact, if you have a leak and maybe you find a path where there's a leak and you'd have to overwrite a stack canary, an SMT solver would be able to handle that if you were very careful about how you coded this. Weird input restrictions, maybe your input has to be all ASCII or something. Computers are actually really great at that because this is just a very simple constraint for something like an SMT solver. Randomization, that's a little bit trickier, but again, this isn't like a fundamental limitation. So let's talk about something a lot harder. So notion of weird machines. So I'm going to actually but use a simple CVE as an example. So this is actually found by Joe Rue back there. It's not a single CVE, it's not a single bug, it's kind of a collection of them. Basically, there's a font driver in Windows, which is using effectively PostScript, and it's effectively using a small programming language to decode your font and render it properly. So obviously this is a terrible idea, but whatever, they're already doing it. But the interesting thing is to generate an exploit for this, the best way, or at least one way, is to create a small program using this PostScript language to then write out a ROP chain. And this is very difficult. So if you think about how to do this automatically, well, maybe you just give this whole program to an SMT solver and symbolic execution and just say like, I'll give you a year, maybe you can work on it. That's probably just not going to work. The encoding is just very inefficient. It's not going to realize what it needs to do because it's not goal-oriented. It just kind of tries to explore things. So maybe you could do something like distill the state machine to a simpler representation, which isn't going to be automatic. But if you did that, then you could probably ask an SMT solver to write a ROP payload. So this would be doable, but this isn't really a general solution. So the problem is that in some sense, proper exploit generation is equivalent to a problem called program synthesis. Here's kind of the Wikipedia thing, but basically it's just generating programs automatically. And as you can imagine, asking a program to start programming is not really great. So it's doable, sure, but it's not a solved problem. It's very far from it. That's basically just strong artificial intelligence. So weird machines happen everywhere, so it's not just these font exploits. I mean, a lot of web exploits require writing JavaScript. In some sense, ROP is kind of like the same flavor. And there's lots of other things that are less obvious, especially in modern exploitation techniques. So recognizing that something maybe encodes some sort of state machine or encodes a programming language, this is actually kind of a creative process, and this is not something that a computer is good at. So that's one issue. Another problem is just finding bugs in general. So we can somewhat talk about a few different types of bugs. So there's maybe bugs you know about. You wrote a program, if the username or something is weird, maybe the program's going to crash, but you just don't care because whatever. There's bugs you don't know about. So these are things like, well, I do a lot of string processing. There's probably some off by one issues here. I've never encountered it, but it probably exists. Or you know about memory corruption or things like that, but you don't know about specific cases for your program. But the real problem is the bugs you don't know about. So this is the sort of thing like rowhammer. A lot of people, if you talk to them 10 years ago and they were analyzing the security of a program, they'd never be like, well, what happens if I write over there and this other DRAM cell bit flips? This isn't something that was included in your security model. So the issue is effectively automatic program analysis is checking against the specification. So normally this specification is very simple. It says, well, your program shouldn't segfault. Maybe it shouldn't print uninitialized memory. Maybe it shouldn't call and execute user-defined code, whatever. You can write more advanced specifications if you want, but that's fine. So the question is, how do you detect bugs that you never even considered? So one answer is you have someone very smart think about this very hard. The other answer is I have no idea. I don't think there's another way of doing this. So that's a big problem for trying to automate this stuff. So there's other issues as well. So if you try to just write maybe a general template for what bugs look like, this isn't always going to work. So maybe you're saying, oh, things in databases should be encrypted. That's not always true. Maybe you can keep UID numbers unencrypted, but if you have, a social security number or other national identification number, that should probably be encrypted. Maybe you have SHA-256, a great algorithm, that's fine. You're using it to hash data, not a problem. But maybe you're using it in an insecure way and using it as a message authentication code, and that's bad. And now the issue is, how do you determine which of these cases it is automatically? Maybe you're reading from uninitialized memory, and that's bad. But maybe you're something like OpenSSL a few years ago, and you need to read from uninitialized memory in order to seed random key generation. And this is terrible, but if you remove it or try to fix it, you might make things worse. So the problem is, again, this is kind of a creative area. So some things might not look like bugs when you first look at them. It could even be the case that there are valid features in a program that can be helpful for generating exploits or making bugs by chaining several things together. So discovering unique bugs in this sense automatically is just very, very difficult. So the last issue is something like intuition. So I would posit that great bug finders aren't always the fastest at analyzing programs. This is with the caveat that I'm not a great bug finder, but if you look at these people, it's not like they say, well, I can analyze 1 million lines of code in a week, and that's why I find all the good bugs. No, they know where to look for bugs, and that's the real trick. So it's not exactly a trick per se, it's actually really a skill. And the issue is this is a difficult to teach knack. So, you look at programs, a lot of people, they say, I think there's going to be a bug here. Maybe you look at a few functions, and that's where the bug is. So automated systems don't really work this way. Effectively, they just try to maximize some sort of code coverage. And this works really well in practice, but it's effectively the strategy of, I'm going to try to analyze 1 million lines of code in a week. And this is great because maybe they'll find things other people would miss, but it's still a brute force strategy. So you're not going to be able to fully analyze something like a browser if you're taking this approach. So an interesting idea here is that guiding, fuzzing, or symbolic execution is something that should be possible. Right now, this is usually basic heuristics, like maybe this block has a bunch of memory dereferences or something like that. But one of the cool things here is that this is a great place for something like deep learning. So hopefully this is something that we'll see in the near future. All right, so at this point, now you're saying, well, this sucks. Computers aren't going to be able to do anything. I don't care about this anymore. We just need humans. So let's talk about the future. So what's going to happen in the future? Singularity is going to come. Computer intelligence will solve all of our problems, but that's probably just because we'll all be dead. Okay, that's probably not what you were looking for. So let's talk about the near future. So let's take a historical perspective. So let's talk about chess. So chess is interesting. So it was kind of one of the original problems that Alan Turing mentioned, where he was like, this is the sort of thing a computer ought to be able to do. And in 1959, they decided, people started saying computer chess would be the world champion in 10 years. People came up with the idea of computer-assisted chess, humans and computers working together. Several years later, 10 years away from being the world champion, 3 years away from being the world champion, and then 8 years later, it actually became the world champion. So, maybe our estimates for how far away things are not very accurate. But the interesting thing is, after this happened, we have these computer-assisted chess tournaments. So this is what's called a centaur. So I don't mean like this kind of centaur. I mean this kind of centaur. So the basic idea is you have computer and human working together to play something like chess. So it turns out this is really interesting. So centaurs actually outperform humans or computers. This was surprising enough to me. I've heard it a few times, but I had to make sure that it was true. I did look it up. Apparently it's true. So if you look at a top computer's ELO ranking in chess, it's some arbitrary number, let's say 3,400. I don't really know what an ELO ranking exactly means, but that's what the internet says. Top human, right now it's about 2,800. But it turns out if you have a human with an ELO ranking of, let's say, an intermediate to above average player, they can actually help a computer with superhuman abilities. And that's crazy. I mean, if I went to a top chess grandmaster and tried to help them at chess, that would not, that they would just tell me to go away. But it turns out that if you have, a computer and human working together, they can actually be better than either one alone. So the first question is, how is this actually different from just people using computer tools? Centaurs sounds a lot fancier. But it's actually a little bit different than that. So these two components could work individually if they wanted. If you were playing Centaur chess and the human dropped dead, the computer would still keep playing. Right now, if you look at something like computer security, humans are really pulling all of the weight. So fine, computers do disassembly, maybe decompilation. They can fuzz stuff, although sometimes people still fuzz things by hand. ROP payload generation, there's some cool tools that can do that for you. But navigating down complex code paths, humans do that. Triaging bugs, humans mostly do that. Generating exploits, humans do all that. So, there's a lot of cool things that centaurs should be able to do. So, first example is, maybe I have a small area of code that my human intuition tells me is sketchy. You can tell a computer, this is the place where you should be focusing your resources, get to this area of code, and try to analyze it more deeply. You can also do something like maybe here's a specific input that will get down this branch. Maybe you have something like an MD5 code that you have to reverse. You're not going to be able to do this automatically with a computer, but maybe you can Google the MD5 code as a human and find out that it was cat or something like that. And so this is something that you could add into a computer that's already running. On the other hand, maybe you're analyzing something and you say, I think it'd be really interesting if this register value was ever able to be -1. Computer, please tell me if this is ever possible. Maybe you're looking at something like use after free or something else, and you say, is there another place where this might be modified? Maybe this will be freed by one thread and used in another or something. Maybe you want to say, can you ever call the same function twice and keep this data alive or something? Maybe you have an exploit and it works some of the time, but you want a computer to do kind of the annoying weaponization task because that's really tiresome sometimes. Or maybe you just want to say, I want to find a large buffer somewhere in my program that I can write to at a known address. So these are all things actually that are pretty close to being possible. These aren't the sort of things that are 10 years away. These are the sort of things that are 3 years away or less. And so honestly, I think that the cooler stuff we haven't really thought about. The cooler ways that you might be able to use the Centaur model in computer security. So I guess I have a few predictions that might be interesting. So first, I think centaurs will probably start to be a buzzword in the next few years, with the caveat that this might be called cyber centaurs. So we'll have to see. Jury's still out on that one. I think people that are doing, the great bug finders who right now are just doing fuzzing, I think they're going to have to start stepping up their game. So this doesn't necessarily mean symbolic execution, but maybe at least something like taint tracking in programs, doing something a little bit smarter, not just using AFL or something like that. I think centaurs are going to be more common. I think this will probably start in CTFs, not because CTFs are magical state of the art, but just because CTF problems tend to be a little bit easier to look at. So I think probably like we saw at this past year's DEF CON, which was modeled with CGC, and a lot of teams were able to use some of the same technology. I think we'll probably see this moving forward. I think we'll see this in more CTFs, which should be interesting. Also, I think automated systems are going to get a lot better. We're kind of at the raggedy car driving through the desert thing, not yet at the Google self-driving car navigating streets. But I think we're going to close that gap very quickly. So just a few conclusions. So as humans, we're still needed, but we also need help in finding bugs. Now, one thing is a lot of people kind of have the opinion like, it's like you're digging your own grave by working on this task, right? You're a computer security person. You're trying to automate your job away. I don't really see it as that. I think computers are going to be needed for a very long time. And I think AI might kill us no matter what, so it doesn't really matter. But systems today, they're not completely magical, but they do a lot more things than you expect. Again, even as someone who developed one of these systems, I'm still kind of shocked at some of the things it was able to do. And there's also a lot of very interesting research still needed. So, if you find this stuff interesting, it's not like you missed the boat and all the research is already done. There's lots of cool stuff to work on. So I'd encourage it. So yeah, at this point, if you have any questions, let me know. No questions. Questions. We'll put a small timeout on this, and then let's say a 30-second timeout. Maybe 30 seconds was too generous. Yes, thank you.
You say AFL just fuzzing. Let's look into the state.
So AFL does So AFL does instrumented fuzzing. It's a great tool. It does very good instrumented fuzzing. If you use some special like compilation passes, some of the things like comparisons, you can break it up from a 4-byte comparison into 4 1-byte comparisons, which is a lot easier to fuzz. But at the end of the day, it's still just a fuzzer, right? It doesn't do taint tracking. It does kind of some pseudo taint tracking, like, oh, I flipped this bit and it didn't do anything, so it's not interesting. But it's still, it's a well-engineered tool, but it's not a very, academic advanced tool, I guess I would say.
Is your team publishing something better?
No, so we're terrible and we don't open source or publish things. So we have our tool and we're hoping to make money off of it, basically. So yeah, sorry, I know it sucks. Yeah.
So I have a question. So for this DARPA contest, that it's completely automated. So like you submit some tools, some code in advance, and then you don't touch anything during the contest.
Yeah. So
there's no human interaction.
Correct. Yeah. So the way that this was implemented was so 7 teams qualified. They actually gave each of those 7 teams a large rack. The large racks were on an air-gapped network. So we put stuff on the machines, a week before. They moved them onto the air-gapped network. And then they pushed some buttons, and we couldn't do anything. So no humans at all.
Okay. So because you mentioned those 2 ways of dealing with the problem, fuzzing and the symbolic, how do you call it?
Symbolic execution.
Symbolic execution. So for the symbolic execution, you can automate all this as well?
Yeah. So yeah.
This seems like it requires some analysis of.
So if you wanted to do something like, say, this is a good place to get to, symbolic executor, take me here. That's the sort of thing that's feasible. However, by default, what they do is they work a lot more like a fuzzer, where it will just say, here's a input to a program. It took these branch conditions. I'm just going to flip some of the branch conditions and generate new inputs, and then iterate through this process. Yeah.
What if you want to go to the next step and say, well, I found a bug. Let's try to remove it.
Yeah, so this is something I didn't talk about, but it was part of that contest. This is doable, sort of. So, for example, our system in this contest had a few things. So it would harden binaries, so do things like add randomization or stack canaries or things like that in a compiled program that didn't previously have them. So that helps make bugs more difficult to exploit, but doesn't exactly fix them. There's a few things that you can do for fixing bugs. So in my opinion, the best way of doing this is something like running the program with valid inputs to generate maybe a range of values for acceptable place. Like, you read from an input, and normally you go through a loop, 100 times because there's 100 characters, and you find out as soon as you hit it 101 times, it crashes. That's something that's actually not too difficult for a computer to infer, as long as it's a simple bug of that nature. And then you can go in, insert, an assembly thing that says, if you ever go through that loop too many times, abort. So there's some work in this area. It's still very early. I think it's very interesting. I left it out of this talk, but yeah, that's something that we're also working on, and other people are working on too, not just us. But was there another? Yeah.
I was impressed by the amount of the prizes that are to win in this kind of contests.
Mhm.
Is there an explanation? Is that because the organizer want to attract more people? Have you an explanation?
Yeah. So I mean, the basic idea is, this was, the U.S. government, so it's a small fraction of their budget. But if you think about something like this, our team effectively had maybe 5 people working full time on this for 2 years, and so the idea, I think, was that a normal company wouldn't take that leap and say, I'm going to work on this in the hopes of it paying off, because it's not clear that even if you get to the end of the road, there'll actually be a big payoff, and so they kind of minimize the risk of doing pure research for a little while. So I think that's why they made the prizes very large. Any other questions? Yeah.
You said that the Mayhem was actually designed to work for standard web files, and so do you actually use it on to search for an actual vulnerability? Have you tried to use it on a CTF or maybe for actually fuzzing a real software?
Yeah, so we've used it for a few things. So we've had customers that have come to us with programs and asked for us to help find bugs. Even some people who have already been fuzzing stuff, we've found some things that they've missed. We've ran it on a couple open source things just with a limited amount of compute time. We found some null dereference in OpenSSL or something like that. We've used it a little bit on CTFs, but CTFs, something like Anger is also very similar. And so a lot of CTFs these days are written in ways to kind of subvert symbolic execution. At least that's what good CTF organizers do, unless they want it to be for something like that. But yeah, so we've used it on real world stuff and it works, not like Chrome, but ImageMagick or OpenSSL or something small. Any other questions? Cool. All right, I guess that's it. So thank you very much. Yeah, if you have questions, I'll be around CTF area /here, so feel free to stop by and say hi.